So now we can say, well, how does it look like? This could just all be nice in a graph, but there is no standard error here. There is no confidence interval. Maybe this is not really very solid. So we can look at that in a regression. So this is a simple regression, which gives us directly the difference. What you can read here is the difference between the log earning of the treatment group and the log earning of the control group. That means I could have plotted bar charts like we had with the bednet. It's saying the control group, this is the mean here in the control group. The mean wage in the control group is 7.8, which corresponds to about the median and about the mode of the distribution, 7.8. And the mean wage for the treatment group is 0.18 percentage, log 0.18, so that means about 19 percentage point higher than the mean in the treatment group. So when we run regression in logs, the advantage is we can read the coefficient directly as the percentage point increase. So if we wanted to know what's the mean log wages in the treatment group, what do we need to do from this graph? Just to make sure that you have it well. Yeah? Go ahead.
Take the mean and multiply by 1.19.
No, so what you would do, you could do this is the mean of the log. And this is the extra log point that they get. So if we wanted to know the log wages for the treatment group, all we would need to do is to add 0.19 to 7.80. So that would be about 8. And then if we wanted to know the level, then we would take the exponential of 8, right? So when you have experiments, you can just take you can calculate the mean in the treatment group or the mean in the control group. But in papers in study, what you generally see is people running a very simple ordinary least square regression of treatment wages, say, on wages of whether you are a treatment person. And the way we read this is just saying this is the difference between treatment and control, and this is the mean for control. And then once we've done that, we can add other things that absorbs the noise, and we'll get slightly different results, but not very different because everything is randomized. What is this one? Right here? What is this little guy in parentheses? Sorry? The standard error, exactly. This guy is the standard error. So this is saying there is some noise around these wages, so the difference with the mean, because we have the distribution of wages, so there is some variation around the estimate, and therefore there is some noise around our estimate of the difference between treatment and control wages, and that tells us the standard error. So if we want to know whether something, so now we need to know, well, how do I know whether this effect is just due to chance or whether it's a real effect? Once I give you the coefficient and the standard error. Yeah?
If it's more than 2 standard errors, isn't it significant?
Right, so it's, if you divide the coefficient by the standard error, it gives you something we call the t-statistic for the hypothesis that the effect is 0. So when we divide the coefficient by the standard error, we get the t-statistic. And the t-statistic is for the test that the coefficient is not 0. So the hypothesis is this coefficient 0? So with each test goes with a size, a level of confidence, which is the probability of a type 1 error. That is the probability that you're saying there is an effect when in fact there is not. Generally in economics, I don't know in other fields, but in economics, generally we go with sizes of 5%. So we accept to say that something has an effect when in fact it doesn't with a probability of 5%. And 5% correspond to a t-statistics of 1.96. So when you see a regression table like this, it's very simple. If things are randomized, when you see a regression table, you're looking at this effect gives you the difference between treatment and control, divided by its standard error. And if it's above 196, it tells you that the effect is significantly different from 0. That is, there is a real effect, not an effect due to chance. So here, of course, it's much above 2. And it's about 19%. So it tells you that the wage of the treated guys is 19% higher than the wage of the control guys, which is a fair amount. And this is, so once it's that, so why do I say that 19% wage is high? What's the economic growth? What was the economic growth in Kenya over this period, give or take? An order of magnitude. 10% would be nice. 10% would be, I don't know if they had any single year where they had 10% growth. Yeah, 3, 4. So that would be in real terms. Yeah, but this is, remember, we are comparing treatment to control. So there is no inflation here. It's our treatment people were measured at the same time. Take real growth, if we're saying 3 to 4% a year, we are being generous to Kenya for the average. So that means that these guys got the equivalent of several years of good economic growth. Except there has not been many years in Kenya where there has been several years of good economic growth. So that's why I wanted to get you excited about worms for 5 minutes. Whether you would think, so this thing corresponds to giving the kids a pill, which costs about, including the delivery cost and all of that, about 60 cents of delivering the pill. You need to do that twice a year. And this is the difference between doing it for 3 years versus 1. So this is, your investment, the public good investment that was delivered by society here in the form of this NGO was, $1.20. And that's 19% per year. That's a lot. Even people, if they had to do it themselves, maybe they have to do to the shop, so they don't get it for 60 cents, they have to pay $1. It's still, then they get several years of good growth for the entire lifetime of the child. So we're talking about, for a lifetime of the child, of several $1,000 of extra wages. And we can see it here. So what this is these are the benefits that you're getting from this 19% increase in earnings. So imagine that you get 19% increase in earnings. Take the GDP of Kenya, so or the average wage level of Kenya, multiply it by 19%. That's how much you're getting every year. Then you have to compute the net present value, because the benefit that you're getting if you have to pay the investment today, but you're starting to get the return when you're 20 and then over your lifetime, it's not as valuable. So we are using some discount rate, let's say 5%, and we're computing the net present value of those earnings like we would for the investment in a stock. So when you do that, you get over $1,000 increasing in your lifetime earning. So this is that, and this is how much it costs. So you need to deliver the pills, $0.65 per year. And then they wanted to, so that would be like a huge benefit of like $1,500 or $1,100 divided by 65 cents. So that would be pretty gigantic. That's why worms are exciting. Well, I don't want to make it too exciting, so they're saying, well, let's see what all the costs we need to add. Well, these kids have gone to school a little longer. They've gone to school more every year. So while they're in school, they're not like playing, or they're not earning some wage. And so they're making some assumption of what is this opportunity cost. At the wage, at the unskilled wage, all of the days they spend in school, they assign them the wage, which is that's an overestimate, because usually the kids are just doing nothing because they're sick. So this is like being very generous for the cost of being in school. And then they also add the fact that if you have more kids in school, you need to have maybe a bit more teachers and all that. So they also calculate how much that can be. So these things are like, you might want to put them, or you might not want to put them. But the bottom line is that when you do that, this bar is pretty huge and this bar is pretty minimal. Yeah.